most startling predictions of the theory of special relativity is that moving clocks run slow by a factor, the square root of 1 minus v squared over c squared. Where v is the speed of the clock relative to the observer, and c is the speed of light. For example, if we had three identical clocks at rest with respect to an observer, and at one moment they read the same, then of course we expect at a somewhat later time they will all read the same again. But if we have the same three identical clocks, but one of them is in motion with respect to the observer, then at the later time, let's say when this one has passed the others, it will read a lesser elapsed time, a shorter elapsed time than the ones that are at rest. As read by the observer, the moving clock runs slow. This effect is called the Einstein time dilation, and ordinarily it's a mighty small effect because v over c for most things is a very small number, so that this whole expression is very close to 1. For example, a clock moving by us in a rocket at 5 miles a second, it loses only 1 second in 100 years. But we do have some clocks that really go fast, that go 99% the speed of light, and they run at a ninth of the rate they do when they're at rest with respect to us. These clocks we're going to show you. These are mu mesons, charged radioactive particles in the cosmic rays. First we have to detect them. So, detect mu mesons. Then we'll stop some of these mu mesons to measure the distribution of their radioactive decay times. As you'll see, this will enable us to use these mesons to measure time intervals. So, distribution of decay times used as clock. Finally, we'll use these meson decay clocks to measure time dilation. We'll compare two measurements of a time interval, the measurement by mesons going at high speeds with respect to us, and the measurement by mesons at rest with respect to us. The mu mesons we'll use are produced high in the atmosphere and come shooting down toward the Earth. As they come down, some of them disintegrate in flight. The number arriving at a high altitude is greater than the number surviving to reach sea level. Right now, we're up on top of a mountain, Mount Washington in New Hampshire. We will count the number of mesons that arrive here, and then we'll go down later to sea level and count the number that survive to arrive there. By comparing these numbers, we will show that these moving clocks run slow.